Okay, so this is our last section in Chapter 4, Section 4.8, which is solving problems with trigonometry. We're going to talk about more right triangle problems and simple harmonic motion. So angle of elevation and angle of depression. So angle of elevation is if you're looking out horizontally and measure upward from that horizontal, that to your line of sight, that would be angle of elevation. If you're looking out horizontally and measure down from that horizontal, that's angle of depression. So it's important to make sure you understand the difference between those so that when you're drawing your triangles and setting up your problems, you correctly draw the picture so that way you get the right answer. Okay, so example 1 says using angle of elevation. So the angle of elevation from the buoy to the top of Barnegat Bay Lighthouse, 130 feet above the surface of the water, is 5 degrees. Find the distance x from the base of the lighthouse to the buoy. Okay, so here's a buoy, here's a lighthouse. So it says that our angle of elevation, so that means from the horizontal upward, is 5 degrees. The lighthouse is 130 feet above the surface of the water, and we're trying to find the distance from the base of the lighthouse to the buoy. So what we look at is we focus on the 5 degrees, and we say, okay, 130 is opposite the 5 degree angle, and x is adjacent to the 5 degree angle. So if we have opposite and adjacent, that tells us we're going to use tangent. So this would be tangent of 5 degrees equals 130 over x. Then this is one where the variable's in the denominator, so we need to multiply by x first. So then we have x times tangent of 5 degrees equals 130, and then divide both sides by tangent of 5. And we get, so 130 divided by tangent of 5 is 1,485.9 feet. Okay, our next one's a little bit more complicated. So it says from the top of a 100-foot air traffic controller, so you can see the air traffic controller would be right here, control tower, an airplane is observed flying towards the tower. If the angle of elevation of the airplane changes from 32 degrees to 10 degrees during the period of observation, and the altitude of the airplane changes from 500 feet to 200 feet, how far does the plane travel? So we're trying to find D right here, how far the plane travels from the first point to the second point. Okay, so what we want to look at here is we want to look at how we have kind of two different right triangles. So the first one that I'm going to look at is this one right here. So if this whole height is 200, that means that we have to subtract out the height of the air traffic control tower. So that would be a height of 100, and we're looking for x. So we're going to use tangent again. So this would be tangent of 10 is equal to 100 over x. So that means we multiply both sides by x, so it's going to be 100 divided by tangent of 10, which is going to be about 567.1. Okay, then we're focusing on, let's change color here. We're going to focus on the bigger triangle. So this one right here. So again, we need to subtract out the 100 feet tall that the air traffic control tower is. So this would be, we're going to say, so we have 32 degrees, so it would be 400 feet would be the opposite side, and then our adjacent side would be x plus d. So we're going to say tangent of 32 equals 400 over x plus d. So if we solve this the same way, so we multiply both sides by x plus d, and then we divide by tangent of 32, that means x plus d, sorry, my dog's being loud. Okay, x plus d would equal to 400 divided by tangent of 32, which is going to be 640.1. So what I really want to find is d. So if x plus d together is 640.1 and x is 567.1, I can take 640.1 minus 567.1, and I get, oops, not 70, I get 73 feet. So again, that one was a little bit more complicated, especially if we had to draw the picture ourselves. So, okay. Our next one is talking about simple harmonic motion. So a point moving on a number line is in simple harmonic motion if its directed distance d from the origin is given by either d equals a sine of omega t or d equals a cosine of omega t, where a and omega are real numbers and omega is greater than 0. The motion has the frequency omega over 2 pi, which is the number of oscillations per unit of time. So here's an example of this. A mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, can be modeled as harmonic motion. If the weight is displaced a maximum of 4 centimeters, find the modeling equation if it takes 3 seconds to complete one cycle. So from this, we know that A, our amplitude, is 4, and we know that the period is 3 seconds. So that tells us that the frequency, remember, is the reciprocal of the period, so it would be 1/3. So from the previous slide, we know that it says here that the frequency is omega over 2 pi. So in order to find out what omega is, we can say, okay, omega over 2 pi is equal to 1/3. So if we solve this through cross multiply, divide, we would cross multiply. So omega would be equal to 2 pi divided by 3. So we can write the equation as d equals 4 sine of 2 pi over 3t. So that equation would describe the motion of the oscillating mass on the spring. Okay, let me know.